Hello and welcome to this lesson for OCR A-Level Physics. In Module 5, the Newtonian World and Astrophysics, in the topic of gravitational fields and on the concept of gravitational potential. So if we've been successful and we've learnt in today's lesson, we should be able to define what gravitational potential is and why it is zero at infinity, calculate the gravitational potential for all objects, and understand what equipotential surfaces are and their importance in gravitational fields. So we're going to be looking at the following part of the OCR A-Level Physics specification, 5.4.4, Gravitational Potential and Energy. Now if we consider a gravitational field produced by a mass, any other massive object placed in the gravitational field will become a store of gravitational potential energy. This gravitational potential energy store is produced because of a resultant gravitational force acting on the object due to being in the gravitational field. So this energy is due to the attraction produced between the masses. Now this gives us the concept of absolute gravitational potential, and this is the gravitational potential energy stored per unit mass due to being placed at a point in the gravitational field. And we give this quantity the symbol V. Now we can set the absolute gravitational potential to be zero at any place, however we choose to set this at infinity, as shown in the following diagram. Now we define infinity as any region outside of the gravitational field. Now we set infinity to have zero absolute potential as the particle or object is outside of the field, so feels no force from the field, and it is no longer a gravitational potential energy store. Now previously we have said that gravitational fields extend out to infinity, so this seems a paradox. However, here, by infinity though, we really mean as far away from all masses in the universe as we need to be to make the gravitational forces negligible in whatever context we are looking at. Now, all masses attract each other, so it takes energy, that is, external work must be done, to move the objects apart. This means that all values of gravitational potential are negative. So we can summarise the concept of gravitational potential as the following: that when an object falls towards a massive object, it will be due to gravitational attraction. Now work would need to be done to pull the object away from that massive object. So the absolute gravitational potential is the energy stored per unit mass in an object due to being placed in the gravitational field. Now we can work it out with the equation V is equal to minus gm over r, where g is the universal gravitational constant. M is the mass of the object producing the gravitational field, and r is the separation between the object in the field and the object making the field. Now this is not the inverse square law. Rather, when the distance doubles, the potential halves. So when the distance trebles, the potential decreases by a third. So we can say that the potential and the separation are inversely proportional. Now gravitational potential is always considered negative on the surface of a mass and increases with distance from the mass. This is because energy needs to be placed into an object to escape a gravitational field, as gravity is always attractive. So, to reach infinity, which we define as zero, we must place a positive value in, so therefore it must start off originally as a negative value. Now gravitational potential is a scalar, as both energy and mass are scalars. Now this makes it one of the only scalars to be given a negative term. Now this equation only works when we consider the mass produced in the gravitational field is a point or a spherical mass. Now please note the minus sign is not optional. All real potentials are negative, and the zero of potential is at infinity, since all objects store no energy gravitationally at infinity. Now the definition of gravitational potential refers to a mass being brought into the field rather than being removed from the field. Now potential, like field strength, is a property of the field at a point and is independent of the object placed there. Two objects with different masses at the same point in the field are subject to the same potential but will have different energies. So, for example, if the gravitational potential is minus 20 megajoules per kilogram, in other words it means it would require 200,000 joules of work to move a unit mass from that point to infinity. Or we could say it would require 40 megajoules of work to move 2 kilograms from that point to infinity. So we can summarise the concept of gravitational potential with the following diagram. Now note, gravitational forces are always attractive, This means that as r decreases, positive work is done by the mass when moving from infinity to that point. When a mass is closer to a planet, its gravitational potential becomes smaller, more negative. Now, as the mass moves away from a planet, its gravitational potential becomes larger, less negative, until it reaches zero at infinity. Now, as we've said, all values for gravitational potential are negative in a gravitational field. However, changes in gravitational potential can be positive or negative depending on the direction of motion. Now, also, when the distance r becomes very large, the gravitational force tends rapidly towards zero at a point further away from a planet. Now, here's an example question regarding gravitational potential. Find the gravitational potential V at the surface of the Earth. The Earth's mass is 5.98 times 10 to the 24 kilograms, and its radius is 6.37 times 10 to the 6 meters. Our first step is to write out the equation, V equals minus gm over r. The second step is to place the values into the equation. V equals minus 6.67 times 10 to the minus 11 times by 5.98 times 10 to the 24 over 6.37 times 10 to the 6. This gives us a value of minus 6.2616 times 10 to the 7. Remember to give all our values to the appropriate number of significant figures with a unit. So our answer is V is equal to minus 6.26 times 10 to the 7 joules per kilogram. Now, the absolute gravitational potential is the energy stored per unit mass in an object due to it being in the gravitational field, which we can show within relationship-wise with the following graph of V against R. Now, if we know that V is proportional to R, so therefore if R doubles, then V will halve. The potential will tend towards towards zero as R approaches infinity. Now, the potential will tend R towards zero as R approaches infinity, which is an important idea, and the most negative value of V is equal to the radius of the massive object. Now, by using tangents, we can find the gradient of any point of the graph, so our gradient is delta V over delta R, which is called the potential gradient. Now, the potential gradient is another name for gravitational field strength, as gradient is equal to V over R, which is equal to Gm over R, so therefore is equal to Gm over r squared, which is equal to the gravitational field strength. Now, changes in gravitational potential are more complex if a number of masses are involved. Now, since gravitational potential is a scalar quantity, the total gravitational potential at any point is equal to the algebraic sum of the gravitational potentials from each mass at that point. Now, a graph of V against 1 over r will produce a straight line through the origin, with the gradient equal to minus gm. So we can summarise the graph of V against R as the following. The key features of the graph are that the values for V are all negative. As R increases, V against R follows a minus 1 over R relation, and the gradient of the graph at any point is the value of G at that point, and the graph has a shallow increase as R increases. Now, the concept of gravitational potential allows us to calculate the gravitational potential energy stored in an object in both a uniform and radial field. Now, we know that gravitational potential is equal to the gravitational potential energy stored over mass. So therefore, we can say that the gravitational potential energy stored is gravitational potential times by mass. So it is minus gm over r times by m. So it gives us our equation of minus gmm over r. Now, we know that the further you get from an object, the greater the energy stored in the gravitational field, as something must have more work done against gravity to get you there. Thus, when you're infinitely far away, you have high an energy relative to it as possible. Now, we choose arbitrarily to make the value of energies of all bodies at infinity zero. Then, since this is the highest value of energy, all real values of energy stored gravitationally must be negative. Therefore, the minus sign in the equation is not optional. It must always be included, and all values of energy stored in a gravitational field are negative. This is not the case when we come to electrical fields, because they can be repulsive as well as attractive. Now, in our equation, we've written energy here, but not change in energy. Now, by defining a point relative to which all energy is measured, we can now talk about absolute values of energy rather than changes in energy, and this point, which we define, is at infinity. Now, the energy stored in an object follows an inverse proportion law and not the inverse square law. Now, on moving away from an object, there's an increase in gravitational potential, so any object moving this way would gain gravitational potential energy. Now, if an object has no change in gravitational potential, there is no change in gravitational potential energy. Moving towards an object results in a decrease in both gravitational potential and gravitational potential energy. So, if we consider a gravitational field produced by a mass, any massive object in a gravitational field becomes a store of gravitational potential energy. Now, this is considered a scalar quantity, as the gravitational potential energy is stored in the object. Now, this can be considered an absolute quantity, as it's not dependent on any other factor except the gravitational field. Now, gravitational potential is the work done per unit mass to move an object from infinity to a point in the gravitational field. Now, at infinity, we've defined the gravitational potential to be zero. This is because the object is not in the gravitational field. Inside the gravitational field, the gravitational potential is non-zero, as it's become a gravitational potential energy store due to being in the field. So our absolute gravitational potential is our energy stored per unit mass due to an object being placed in the field. Our gravitational potential is the work done per unit mass to move an object from infinity to a point in the gravitational field. So, if we say that gravitational potential is the work done per unit mass in moving an object into the gravitational field from infinity, this means that the gravitational potential and the absolute gravitational potential will always have the same magnitude. Now, this leads to a fundamental concept in physics. Moving an object into different values of potential need work to be carried out. So if we consider a gravitational field produced by a mass, we can see here this is an example of a gravitational potentials found in the Earth's gravitational field. This allows you to understand the concept of gravitational potential in terms of energy stores. So if you let 1 kilogram drop from infinity to the surface of the Earth, it will lose 63 megajoules from its potential energy store. This is ignoring dissipant forces, and the object will have that kinetic energy store when it hits the surface of the planet. So to summarise what we've looked at in today's lesson, gravitational potential at any point is as the work done in bringing the unit mass from infinity to the point, and the gravitational potential is zero at infinity. The gravitational potential is equal to minus gm over r at a distance r from a point mass m, and that leads to changes in gravitational potential. Whilst the gravitational potential energy is equal to mv, which is equal to minus gmm over r at a distance r from a point mass m. So if we've been successful, and we've learnt in today's lesson, we should be able to define what gravitational potential energy is and why it is zero at infinity, calculate the gravitational potential for all objects, and understand what equipotential surfaces are and their importance in gravitational fields. So thank you so much for watching this lesson for OCR A-Level Physics. In the Module 5, Newtonian World and Astrophysics, in the concept of gravitational fields, looking at our topic of gravitational potential. Thank you so much for listening, and as always, have a lovely day.